Hello, my name is Sakib Karim and I'll be presenting the boost converter with feedback. The design objective is to create a voltage mode boost converter using feedback to maintain a fixed output voltage with varying input voltages and or loads. The voltage loop compares the output voltage with a voltage reference to provide an error signal generated by the error amplifier shown here. And the error signal is then applied to a comparator and which is then compared against a sawtooth waveform, which is being generated by a square wave in an integrator. The output of the comparator is a varying PWM signal applied to the MOSFET driver circuit shown here, and then to the MOSFET itself. So when the input voltage and or output loads change, the PWM is then adjusted to maintain that 10 volt regulated output. So the boost converter is just a step-up DC-DC converter, which utilizes an inductor, MOSFET, a diode, and an output filter capacitor, and a load. So when the MOSFET is in the on state, the inductor current increases with the diode in the off state. And when the switch is in the off state, all that stored energy from the inductor is then released through the diode and then to your output RC circuit here, which results in a higher voltage from the input shown here. And so the load will consist of varying resistances ranging from 1 kiloohms to 47 kiloohms. For the demo, I will be using a 5 kiloohm resistor and a 10 kiloohm resistor. Now moving on to the error amplifier circuit. So the output of the boost converter is applied to a voltage divider, which is then applied to the inverting input of the op482, which is acting as my error amplifier or my differential amplifier. The non-inverting input is a voltage reference of 3.2 volts. And so the difference between these two voltages will create my error signal at the output, which is then applied to my comparator. And the way the op482 is being powered, it is single supply. I am using a 12 volt power brick, and the negative supply is grounded. So you can see here that the error signal being generated by the error amplifier is being applied to the non-inverting input of the LM393, which is my comparator. The inverting input is a sawtooth waveform, so before I discuss the comparator logic itself, I'll discuss how the sawtooth waveform is being generated. First, I'm using a 8654, which is a voltage to frequency converter, which creates a square wave. So the converter itself has an input amplifier, an oscillator, and then a high current output stage. And the way that the frequency is generated is just these two components here, which is a timing components consisting of a resistor and a capacitor. So in terms of how the 8654 is being powered, is that 12 volt power supply, that power brick. What you'll notice here is that there's an input of 5 volts. So basically I'm trying to generate a output signal of 5 volts as well. So it'll be a 5 volt, hopefully a 500 kilohertz square wave being generated at the output. The limit of this 8654 is 500 kilohertz. I am kind of pushing it in terms of its rating. So the square wave is then applied to this integrator configuration, still using the op482 single supply. And so the integrator itself uses a 1 mega ohm resistor at the inverting input with 2 components for feedback. One is another 1 mega ohm resistor, and then a 10 picofarad capacitor. So basically, with the square wave input in this integrator configuration, this will generate a sawtooth or a ramp output from this op amp. So now we've talked about the sawtooth generation being applied to the inverting input. In terms of how the PWM is being generated, basically when the output of the error voltage of this error voltage here is lower than the sawtooth signal shown here, the output is connected to ground. And when the output of the error voltage is higher than the sawtooth, the output is connected to VCC. So this is generating a varying PWM signal, which I will showcase in the demo. Now this PWM signal is being applied to a MOSFET driver circuit shown here. And so the purpose of this driver circuit is just to provide effective switching, apply the proper gate voltage, and then isolate the MOSFET from the PWM comparator circuit from the previous image that we saw. And so the output of this driver circuit is able to provide up to 4 amps of current at the output stage. And the voltage will be approximately its supply voltage, which is at 12 volts. In terms of limits for the IRF 510, there is a max current limit of 5.6 amps, so I was able to rate the MOSFET driver appropriately. I'll go ahead and move on to the actual demo, and I'll see you there. Okay, so transitioning from the previous LT Spice schematics is the breadboard implementation shown here. So in terms of the breadboard, you can see I have that 12-bit brick power supply that we've been using. We also have a DC-DC converter being used to drive the AD654 voltage to frequency converter, as well as acting as my pull-up voltage for the output of the comparator. This 14 dips package here is the OP482. Next to that is the AD654 voltage to frequency converter. And next to that is the comparator. And then after that is the MOSFET driver. And now the boost circuit itself is in this kind of quadrant here. So we have the IRF 510 here, the inductor, the diode, and then your output capacitor, and then your output load resistance. So in here we have the voltage divider, which is being applied to the OP482 error amplifier that we discussed from before. So in terms of other parts of this setup, I have my digital multimeter here, and then the a power supply over there, as well as the waveform application. So go ahead and hook this up so you can see the output voltage being applied to the boost converter. And you can see here at the DMM that it's at 9.48. However, if I do increase my my input voltage here to, let's say, 2, you can see kind of goes to 10.11, and then we'll go to 3.3, and still remains around 10 volts. So in terms of requirements for the project, it is still maintaining roughly around 10 volts. What I'll show here is the waveform for the comparator output when we were talking about the PWM signal varying from the different inputs. So I'm going to go back to 1 volt here. And you can see that the PWM signal is operating right around, I want to say 78% duty cycle, right? You can see that in the waveform. That top waveform is just the output of the boost converter. So you can see it's around 9.5. So when I increase the input voltage, you can actually see the comparator PWM decrease. So right now it's at 35%. And then I'm going to go to 3.3 here. And now it's decreased to roughly about 20% duty cycle. You can even see the waveform decrease as well. So that's kind of the main operation, right, about the PWM varying to apply or maintain that regulated output at 10 volts. In terms of other significant waveforms, so just wanted to show the voltage to frequency converter output. So I'm gonna take away channel 2 here, but this is the voltage to frequency converter output. You can see it's roughly around 5 volts. But one thing I want to point out, since I am pushing this kind of towards the limit of the component itself, there's a little bit of a distortion at the top there. Yeah. Now I'm going to go ahead and switch to a higher load, which is 10 kilo ohms, which I have here. So let me go ahead and do that. Okay, so I switched to 10 kilo ohms. Gonna go ahead and run it again. I'm just switching the DC power supply back to 1 volt here, and then changing the waveform back to this output. Okay, so moving back to the waveform, you can see that I'm at 9.8 volts here. Same with the waveform. You can see some ripple coming from the boost converter. In terms of improving that ripple, if I did a more improved implementation, probably do like a type 2 or a type 3 compensator for the error amplifier. But since this is more of a simple implementation straight away from that, so I'm at 9.8 volts, like I said from before, 9.85. 1 volt for the DC power supply. Sorry, I have to keep going back. The outlet's like right there. Okay, so let me switch this to 2 volts, and I will maintain it here. So this is me switching to 2 volts. You see it's around 10.2. And then we're at 3 volts. Let's do 3.3. It's only around 10.3. So that 10 volt approximately is being maintained by the circuit, and you can see I'm at 3.3 volts right now. And that's pretty much it. Thank you for watching.